So we've talked about measures of center, we've talked about measures of dispersion, and finally we are talking about measures of relative position. So there are four things to talk about in this section. The first is percentiles. The second is quartiles. Then the 5-number summary, which I always say as 5-number summary because I just can't say that well. Talking is hard. And then finally is the standard scores. So, percentiles is something that you've probably dealt with in your life before. A lot of times, if you've taken any standardized testing in the US, we like to talk about the percentile score of things. If you've ever done some sort of like percentage-based personality test, they always talk about what percentile you are in a given category. Scores, I know SAT scores and ACT scores are always given in percentiles as well. So this is just a way to categorize and divide our data, to be able to talk about them, to have some relative context. So to find the value for the pth percentile, the location L is n times p over 100, where L is the location of the pth percentile in an ordered array. I wanted that O capitalized too. So this is a big thing most students forget as we get further into the class. When you're doing percentiles, you need to order your data first. And of course, n is the sample size. So there's a couple rules here. If the formula results in a decimal, the location is the next larger whole number. And if the formula gives a whole number, then you take the data value at that location and the very next one and average the two. And the reason for that is just because the percentiles aren't going to be perfectly lined up ever. So when you get that decimal, you're getting that imperfection kind of showing itself here in the calculation of L. When you don't get that decimal, it means that you're missing a little bit, so we average the two just to be safe. So let's do a couple examples here and finding first the 10th percentile, then the 20th percentile from this stem and leaf plot. So just reiterating, this is gas mileage. Our key tells us 12, column 1 is 12.1 miles per gallon. So down here, 19, we have 19.0, 19.0, 19.1, 19.1, and 19.2. Okay, so let's look at A. Our N is 51. I've counted these up in advance. Our P is 10. And so L is 51 times 10 over 100, which is 5.1. So we're going to take the next largest, the sixth value. And the sixth value is 1, 2, 3, 4, 5, 6, which is 13.4. So this is the 10th percentile. Location. So then in part B, if we want the 20th percentile, N doesn't change, it's still 51. P changes to 20. So L is 51 times 20 over 100, which equals 10.2, just 2 times this number. And so we need to take the 11th data value. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is 16.5 miles per gallon. And this is the 20th percentile. not location, that's the actual value now. The location is the 11. So percentiles are not terribly difficult to calculate. You just have to remember the two little rules here. Take the next larger whole number if you get a decimal. If you don't get a decimal, then you take the value at that location and the next one and average them to get that percentile. So a little bit more about percentiles here. Given a particular data value, the pth percentile that the value is in, that value is in, is P equals, that's the wrong color, P equals L over N times 100. So this is just solving that original equation for P instead of L. Again, where P is the percentile, L is the location of the data value in the ordered array, and N is the sample size. So sometimes you want to know what percentile a data value is. So once you've ordered them, you count what thing it is and then times by 100. So quartiles. Quartiles are called Q1, Q2, and Q3. Q1 is the first quartile, and 25% of all the data values are less than or equal to this value. Q2, the second quartile, is 50% of all the data values are less than or equal to that value. And Q3 is the 75th percentile of all data, and so 75% of all data values are less than or equal to this value. So Q1, I said it already, is 25th percentile. Fifth. Q2 is the 50th percentile. And also, I will put exactly equal to, approximated by the median, because the median is a decent geometric center. And Q3 is the 75th percentile. So the reason we state it this way is because there is no difference in computing a quartile versus the equivalent percentile. So if you need Q3, you just compute the 75th percentile. So let's talk about the 5-number summary. I did it. I knew I was going to do it. So the first number in your 5-number summary is the minimum value. In the data set. The second number is then Q1. The third number is Q2 or the median. The fourth number is Q3. And the fifth number is the maximum. Value in the data set. And we typically write 5-number summaries in a special diagram, a special chart. It's a box and whisker chart. So if you haven't seen one of those before, don't worry, we're going to go over it. So we're going to write the 5-number summary for the previous example. So the previous example, being this one, are gas mileages. So there are 51 values. The lowest value is 12.1. The highest value is 29.1. So our min is 12.1. Our max is 29.1. So then Q1 is 51 times 50 over 100, or is located, I'm sorry, not 50, 25. And this is 12.75. Let me just double check that real quick. 12.75. Q2 is 51 times 50 over 100, which is 25.5. And Q3, 51 times 75 over 100, is 38.25. So this means for Q1 we're going to take the 13th value. For Q2 we're going to take the 26th value. And for Q3 we're going to take the 39th value. So I've already looked up what those values are. Q1, we'll talk about in a second, but this is what a box and whisker plot looks like. So you draw a box, and then it's going to have two lines coming out. So the way our 5-number summary looks like, this is always Q1, this is always Q3. So Q1, the 13th value, is 16.6. Q3, the 39th value, is 24.3. And Q2, the 26th value, or the median, depending on what you use, is 22.3. So when I place 22.3, I'm going to draw another vertical line, but I want to make it match our value. So 22.3 is 2 away from 24 and 6 away from 16, so we're going to put it over here like this. And this is Q2 at 22.4. 22.3, sorry. And now we put our max and our min. So our min is 12.1, it's about 4 away. So I'm going to put it out to here. This is the min, 12.1. Our max is 29.1, it's about 5 away. So just slightly longer. This is the max at 29.1. So this is the 5-number summary. This is how it works. And it always looks like this in box and whisker. Sometimes you may just list the numbers, but more often than not, we're going to write these charts like this. So the next thing that goes with a 5-number summary, is the interquartile range. The interquartile range is the middle of the data, is the range of the middle of the data, I should say, and is calculated by IQR, interquartile range, equals Q3 minus Q1. So if we wanted to find the IQR of the last problem, we have 24.3, excuse me, minus 16.6, and this equals 7.7. So that's our IQR, and a lot of times you will see on a 5-number summary an IQR attached, 7.7, so you don't have to guess. So it tells you how spread out this middle is. This is a companion calculation to the regular range in that it tells you, the range tells you how spread out the entire data is from minimum to maximum. The IQR tells you how spread out the middle is. So if your IQR is a large number compared to your regular range, then you know that the middle of the data is where most of your data values are. If it's a small value compared to your regular range, then you know that more data points are outside the interquartile range than are inside. So our last measure of relative position is the standard score, otherwise known as the z-score. Z-score is arguably one of the more important measurements that we use in statistics, and it measures how far a value is from the mean. So the standard score for a population is given by z equals, and this is why it's called z-scores, because it's the variable we use, x minus mu divided by sigma. So it's x minus the mean, where x is the data value in question, mu of course is the population mean, and sigma is the population standard deviation. So it gives you a true distance in terms of means. The standard score for a sample is still z, and equals x minus x bar over s. Again, x is the data value, x bar is the sample mean, and S is the sample standard deviation. So this is one of our more important values that tells us how far away we truly are, standardized to the mean of our data set. So we're going to calculate some z-scores to end this section. Z-scores do not go away. They will come back over and over and over again, so get used to them. So we're going to calculate z-scores for the math SATs, whose mean is 500 and has a standard deviation of 150. So A, z equals 630 minus 500 over 150. That gives us 0.87. So this is above the standard deviation. Oh, I'm sorry, above the mean, because it's positive. Our 0.87 is positive. B, z equals 630. Not 630 anymore, 290. Losing my mind a little bit. Minus 500 over 150. This gives us negative 1.4. This is below. I don't know why I'm doing arrow and a parenthesis. The mean. For C, z equals 440 minus 500 over 150. This is negative 0.4. This is below the mean. And D, z equals 375 minus 500 divided by 150. And this equals negative 0.83 below the mean. So I keep saying above the mean, below the mean, below the mean, below the mean. And what we mean by that is how many standard deviations we are. So you can add a little note up here. This measures how far a value is from the mean, and this is measured in standard deviations. Same thing here, measured in standard deviations. So when we say the standard score for 290 is negative 1.4, that means we are 1.4 standard deviations below the mean. So if your standard deviation is 150, it takes us 1.4 times 150 to get below 500. Same thing with the first one, part A, 0.87. This means that we are 0.87 standard deviations away, so we're less than 1 standard deviation away. And so this connects back to our empirical rule, which tells us how much data falls where. So since this is less than 1, this falls in with the majority of data. It falls in with 68% of the other data. Same thing with the rest of them. So z-scores are important in that they take our mean, which is our center, our middle, most of the time, our standard deviation, which tells us how far away from the mean we are, and creates a distance unit. It literally turns standard deviations into distance units. So 0.87 standard deviations away means it's above 0.87 times 150. So again, z-scores are not going away. They're going to pop up in the later chapters especially. We start doing a lot with z-scores, but that is the end of 3.3, and with it is the end of chapter 3.